Okay, so today we will be discussing about the remaining portion um, that we left in the previous class. So if I just refresh what we have studied in our previous class, we discussed about generally the working principle of positive displacement machine, okay, and particularly about the reciprocating air compressor, okay, and then we showed uh, you know um, the diagram or the cycle upon which the reciprocating this air compressor works, okay, and obviously we discussed about um, what is indicated work, R power, okay, and how to calculate that. So, and also sort some examples. So that was actually because that was actually the one of the analysis objectives. So if you remember in the previous class, there was a slide where we talked about the analysis objectives. That what are the analysis objectives that you are analyzing the reciprocating air compressor. So we need to know about the pressure and temperature before um, compression process, and then temperature and pressure after compression process, and then we talked about how to calculate the indicated work or power, and then after that we talked about the FAD, that is the free air delivery, etc. Okay, and obviously the important thing for any mechanical installation or machine, that is the efficiency. Okay, so mechanical efficiency. Okay, then after that, if you remember, I told you that as far as reciprocating air compressor is concerned, we need to talk about three, four things. Okay, one of them is, or it was basically that we discussed in the previous class, is reciprocating air compressor without clearance volume. Okay, and then we left with reciprocating air compressor with clearance volume, and I also told you that we will be discussing about multi-stage compression. Okay, so the first portion, it was completed in previous class. Now after discussing some of the slides and some of the things, we will discuss rest of the two bullets. Those were reciprocating air compressor with clearance volume, and then why we need multi-staging and what is a multi-stage compression. Okay, so today's discussion will be about that thing, right? So you see here, there is a topic that is condition for minimum work, right? The first thing you need to know that compressors are power consuming devices, right, as I told you and I am telling you. So uh, work consuming or power consuming device. So being an engineer, what you need to do is, if there is an equipment that consumes power, so we try to decrease that power consumption, right? And as far as the power producing devices are concerned, somehow we do something with the machine that can increase the power output. So in case of power producing devices, we want to maximize the output. In case of power consuming devices, we want to minimize that power input. So this is actually, this idea is about that thing. Okay, so condition of minimum work. What will be the condition, okay, that you can apply and the work consumed by the compressor will be minimum, right? So you can see, it is desirable to have work done on air, that is known as indicated per mass unit mass flow rate, that will be indicated power, to be as minimum as possible. Okay, So they are saying that recall that the indicated work equals the area under the indicator or PV diagram. Previously हमने discuss किया था. The indicated work is minimum if the area under the diagram is smallest. It is very simple, right? That the indicator diagram, that is the PV diagram. Okay. The area under this PV curve, okay, that is basically the work consumed or the indicated work. Okay, so if this area is minimum, consequently the work consumed by the compressor will also be minimum, right? So let us see that how we can minimize this work consumption. So you can see here there are three things. Okay, you know very well that this is constant pressure induction process. This is compression process, the middle one, polytropic compression process, A to B. And B to C is the constant pressure uh, delivery process, right? Now, there are several ways to decrease this area under the curve. One is that if, for example, you take this line to this position, okay, let's say for example, similarly you can take this line from here to this position. Okay, so you can see that you can decrease the area under the curve and consequently work consumed by the compressor, right? But these two things are actually not possible. Okay, or you can say they are not practical. Okay, let us talk about P2. If you are taking this line from here to here, you are basically compromising on this delivered pressure, which is not, which is not required. We want that the pressure of the working fluid, that is here in this case, to be P2, that is this one. Okay, we don't want to compromise on that. इसको हम कम नहीं कर सकते, right? Similarly, this is actually initial pressure before compression. So this means that actually these two, amendments or changes or alteration, they are not possible. Now the third one that is remaining here, this is basically somehow you can do something with this compression process. Okay, so you can see here this line AB. Okay, this one, this is polytropic compression where PVN is equal to constant, right? This AB1, okay, this is this is isothermal process, right? That is PV is equal to constant. That is, this is isothermal process, right? And similarly this one, A to B2, this AB2, this is a PV gamma is equal to constant, that is isentropic process. So we have isentropic compression, isothermal compression and polytropic compression, and you see that area under the curve for this isothermal process is the minimum one, right? This will be the minimum area. This one is you can say that this is greater than isothermal process, and for isentropic process this is even greater. So to summarize it, if you want to minimize the work consumed by the compressor in this reciprocating air compressor, this process of compression should be what? Should be isothermal process. ठीक है, ये क्या प्रोसेस होगा आपके पास? दिस विल बी isothermal process. ठीक है. So somehow if you can achieve this PV is equal to constant isothermal process, तो आप इस area under the curve को and consequently work consumed by the compressor, इसको जो है ना आप minimize कर सकते हैं, right? तो ये आपके जहन में हो. Then we will discuss that it is a bit difficult to achieve this process, okay, in a single cylinder, so we can actually move to multi-stage compression, but that is actually discussion in the later slides. Now this is actually the black and white what we have discussed orally. The height of the PV diagram is fixed. ये height का कह रहा है PV2 का by the required pressure ratio. भाई आपको ये pressure ratio चाहिए, that is P1 P2 by P1. If you change this P2 to this, let's say P2 bar divided by P1. Now this is not the required pressure ratio, right? So we are basically compromising on this one. The length dA is fixed by the stroke of the piston. Now this is the length dA, right? This is the induction value. We can also have this here. So this is actually this is this is also fixed, right? Because of this piston stroke or the cylinder volume, right? So thus they are saying that the area under the diagram will be smallest only if the compression process is carried out in reversible isothermal process according to the law in this one, where the polytropic index is a 1, right? In if you take this equal to 1, right, so this will be PV is equal to constant. Okay, so the summary of this slide is, you can see in the indicator or the PV diagram, if you somehow can achieve the isothermal compression process, you can decrease the area under the curve, and ultimately the work consumed the power consumed by the compressor will be minimum. So that is basically condition of for minimum work, right? They are also explaining that the area in the same diagram, okay, they are referring to this indicator diagram. The area under the diagram will be biggest only if the compression process is carried out in isentropic process, where n is equal to 1.4. So n is equal to 1 के लिए isothermal minimum power work consumption, n is equal to gamma is equal to 1.4 के लिए आपके पास जो वर्क कंजम्पशन है वो ज़्यादा होगा. इट आल्सो कैन बी कॉल्ड रिवर्सिबल एडियाबेटिक और आइसेंट्रोपिक process. The area under the diagram will be moderate when the compression process is carried out in the polytropic process, where n is equal to n. So the best one is the isothermal process, right? We can also look at this one, okay. This is the PV diagram जो हमने discuss किया है, and this one is the TS diagram. You can also look at this one, right? That this is actually in this this is isothermal process. This one is a polytropic process, and this one is isentropic process. Okay, and the work consumed will be less for the isothermal process. Okay, and similarly, you can see that in isothermal process, temperature T1 and temperature T2 bar, they are the same. T1 and T2 bar, they are the same. So this means that it is having complete intercooling process, right? The pressure increases, but the temperature remains the same. Pressure increase होता है P1 से P2 तक, right? But the temperature remains the same. Okay, and that is actually what we want, right? Because if you remember, I told you and I used to tell you that when in the compressor the pressure increases and undue temperature also rises. That undue rise we are actually restraining over here, okay, or we are restricting it over here. इसकी वजह से जो आपके पास जो वर्क कंजम्पशन है जो कि फ्रैक्शन में लगती है, टेम्परेचर को इंक्रीज करती है, वो फ्रैक्शन वर्क जो है ना वो मिनिमाइज हो जाता है, राइट? ओके, सो ऑब्वियसली we developed the formula for indicated work and similarly indicated power for polytropic process. Now if you use the condition of for minimum work means isothermal process, ठीक है, तो उसके ऊपर जो है ना आपके पास जो what will be the work consumed by the compressor. So actually here it is discussed in this slide. The indicated work when the air is compressed isothermally is given by what, area A B1 CDA. A B1 CDA. This is actually that area under the curve, right? And these two are actually the same, but maybe you know about this thing. As I told you earlier, that area under the curve for isentropic process, polytropic process, and isothermal process, they are different, right? So for polytropic, if you remember, we discussed that that is n by n minus 1. I think that is a P2V2 minus P1 V1, if I correctly remember. Previously हमने discuss किया था इसको. This is for what? This is for polytropic process. For isothermal process, it is like this. Okay, it is actually this one. कहाँ से आपको मिलेगा ये आप देख लें. अच्छा, जो different processes है area under the curve, उसमें जो है वो किसके बराबर होता है. Anyway, और इसका proper mathematics है, ठीक है. ये कोई उसमें they are basically using integrals etc. to derive this formula. P2 VB1 log of P2 by P1. That is what? That is your work in the isothermal process. Okay. Right. So you can say that this you can PV is equal to MRT के बराबर होता है. तो ये जो है ना equation 10 आप ले सकते हैं. And they are saying that when M and VA are the mass and volume of air induced per unit time, equation 9 and 10 give the isothermal power. So this equation 10, right, it gives you indicated work per cycle. Similarly, if you take that equation in polytropic process, so that also gives you indicated work per cycle. And the work consumed by the compressor, okay, for this using this equation for the same pressure ratio will be less than for the one that we discussed earlier. इसमें जो है ना work consumption शायद कोई example है भी, मेरा ख्याल है आगे उसमें जो है ना work consumed by the compressor if the process is isothermal is less than when the process is polytropic or isentropic. So if the process is thermal, this is the relationship or this is the relevant formula to find out indicated work per cycle. And the one that we discussed earlier is for polytropic process, right? And in the same way, we are basically repeating things. Okay, previously we also have this isothermal efficiency, but similarly mechanical efficiency, but the process was polytropic. Now if you want to find out isothermal efficiency based on the indicated diagram, that will be isothermal efficiency. The work consumed or the power consumed by the compressor when the process is isothermal. ठीक है, let's say इतना power consume करता है. And the power consumed by the compressor when the process is polytropic. तो वो लेट से आपके पास y है. इन दोनों का जो रेशो है ना, ये कम होगा. अच्छा, ये वर्क कंज्यूम्ड कम होगा, अभी हमने डिस्कस किया है. तो कम बाय ज़्यादा आपके पास वो है कुछ 0.8, 0.9, 0 पॉइंट समथिंग, ये जो है 90% इफिशियंसी आएगी आइसोथर्मल इफिशियंसी. क्यों हम 100% आइसोथर्मल इफिशियंसी को नहीं अचीव कर सकते, दैट इज़ अनदर डिस्कशन. ठीक है, exactly and completely reversible isothermal process is very, very slow in nature and it is not practically possible. So for that reason you need to have isothermal efficiency. ठीक है, मैंने आपको बताया था कि एफिशिएंसी की बात वहाँ पे आती है जब आप डिविएट करते हैं फ्रॉम आइडियल बिहेवियर से या 100% एफिशिएंसी से. बहरहाल इसकी समझ आपको आ गई है. ठीक है, एक एग्जांपल है, कैलकुलेट आइसोथर्मल एफिशिएंसी ऑफ compressor given in example 2. Okay, there was an example 2 in the previous lecture, and over there we found out the work consumed by the compressor, and similarly we also have those efficiencies etc. So they found out the mechanical efficiency. Okay, so the work consumed by the compressor in polytropic process is there, right? And you can find out the work consumed by the compressor when the process is isothermal, and just divide this one that you calculated now by the one that we have in our previous example. you can get the isothermal efficiency. ये solved example है, आप खुद से कर right. So the condition for minimum work की समझ आपको आ गई कि भाई if if you want to decrease the work consumed by the compressor, that actually we want, okay, in order to increase the efficiency. There are different possibilities, but some of them are not practically possible. Okay, as far as the indicator diagram or the PV diagram is concerned, we can do alteration over there. We can decrease the length of a line. You can take the line P2 down there, but they are not practical, right? So the one that is practical and it is mostly achievable is to change the process from polytropic to isothermal, and that's way you can get the the minimum work. Okay, and that is depicted and explained in example 3. Okay, where previously for the same data and for the same pressure ratio, the work consumed by the compressor is calculated, and then the isothermal power is calculated, our work is calculated, and then they found out that the isothermal process, the work consumed is less is opposed to the one that we calculated earlier for polytropic process, and we will be having some isothermal efficiency. That's it, right? Then after that, as I told you that we need to discuss the other bullet, and that was what air compressor with the clearance volume. And if you remember, I told you that air compressor without clearance volume is not a practical case. ठीक है, क्यों नहीं है वो अभी हम डिस्कस करते हैं, right? What is clearance volume? Or in other words, I should say why clearance is needed. Okay, तो बाद में हम डिस्कस करेंगे. It is a spacing. What is clearance volume? It is a spacing between the top of the piston. Top of the piston जो है ना वो ये है क्या? And the piston is moving in this direction. Okay, and it comes to this point. What is this point? ये आगे डिस्कस करता है. And the valve head, ये वाल्व का हेड है. When the piston is at the end of delivery stroke, right? So let's say for example ये यहाँ से आता है. Let's say for example it comes here. Okay, and when it comes to this position, it has developed the required pressure. Now the movement from here to here, it will deliver that pressure. Okay, ये थोड़ा सा एक्सेजरेट करके मैंने बताया है, ये असल में इतना होता नहीं है. It is not like this. It is we are having clearance volume, very small clearance volume. Okay, about 6%. But anyway, I just exaggerated this. So now it is now from here it is starting delivering, or it starts delivering the the air, okay, at that required pressure. And when this piston comes to this point, okay, this position, it has delivered all the pressurized air, okay, except the one that is trapped in the clearance, right? So now at this position, when the piston is is at the end of the delivery stroke, ये delivery stroke है ना, यहाँ से ये delivery start हो जाता है ना, you remember, right? Because this is induction, compression, and from here delivery starts. This is delivery stroke. So not at the start of the delivery, but at the end of the delivery stroke. So the distance between this is the space between the piston head and here the valve's head, okay, at the top of the piston and the valve heads, इसको हम कहते हैं clearance volume. So this will be your clearance volume. बात समझ आ गई? तो ये चीज़ सिर्फ ज़रूरी है. The definition is simple. The space between the piston, the top of the piston and the cylinder head, this valve head, this space is basically your clearance volume. But when, not all the way, right, or for all the position, when the piston is at the end of the delivery stroke, और end of delivery stroke क्या है, वो ये है. तो ये जो आपके पास स्पेस बचती है ना, इसको हम कहते हैं क्लियरेंस volume. अच्छा, फिर कहता है कि गुड क्वालिटी की मशीन्स हैज, ये डिपेंड करता है डिज़ाइनर के ऊपर कितना क्लियरेंस रखता है. अच्छा, गुड क्वालिटी मशीन्स हैज़ clearance volume of about 6%. 6% ये होता है, लेकिन it depends. But compressor with clearance of 30 to 35% is not hard and fast. It depends on the design. ठीक है? Why? Because the motto for clearance volume is actually different. ठीक है? क्यों इसके लिए ज़रूरी है? Remember, बल्कि यहाँ पे शायद we will see, बल्कि ये है भी. Why this clearance is required? So there are actually three things. Okay. One, clearance volume is required for the following reason. One is give a mechanical freedom to the moving parts. Look, यहाँ पे अगर आप ये इसीलिए मैंने आपको बताया था कि this is actually without clearance volume is not a practical case. As I told you, if you see here, this is actually wall up there, and particularly this one is the wall down there. Okay, so if there is no clearance, how this wall will open? ये वाल कैसे ओपन होगा? तो इसको हम कहते हैं मैकेनिकल फ्रीडम टू दिस मूविंग पार्ट. ये वाल मूवेबल है ना, दिस वाल इज मूवेबल, and the motion of this wall is only possible when it is having some space over here. So one is that we don't want to constrain the motion of this wall, but to give a mechanical freedom to this moving part, we need to have some clearance. तो एक तो ये वजह है, right? दूसरी वजह क्या है? Reduce noise and vibration during operation. It is very obvious that if, for example, the piston is moving from here and it comes to this position and again it is coming here, so it will actually all the way be in contact with this wall, this head. Okay, तो ये all the way जितनी भी स्ट्रोक करेगा ना, डक 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 करके ये इसके साथ जो है क्या करेगा, ये in contact होगा. So it can produce wear and tear, it can produce vibration, etc. Right, and ultimately it can even wear the wall and the head. Okay, तो इसलिए जो है ना हम क्या करते हैं कि to avoid this contact of the piston and this cylinder head, okay, or this wall head, we want to have or we need to have this clearance volume. दो चीजें हो गई. And the third one is prevent damage to moving parts. Very simple. This is actually related to even the first two, that it is constantly in contact, it can damage the part. Okay, because there is a there will be bearing stresses, okay, all the way. So for that reason, if you want to have these parts damage free, so you need to have this clearance over here. ठीक है? So this is basically the requirement part. तो clearance की required clearance हम इसलिए रखते हैं. Now from now onwards, remember that we have developed relationships and we discussed about different things for the previous case, and that case was reciprocating air compressor without clearance volume. ठीक है? तो अब हम with clearance volume करेंगे ना, we will not be going into too much detail, but we will be just changing and altering those relationships. ठीक है? So you can see here almost this is the same diagram, okay, but a little bit different. How it is different? Because of this clearance volume. So you can see here, one is that there is over there we were having induction, compression, and delivery stroke, right? So 3 strokes were there. Now here we'll be having 4 strokes: induction, compression the same way, delivery, and then expansion. क्या है ये? Expansion. तो ये expansion का जो stroke है ना, this is extra. Expansion you know very well. High pressure से जब low pressure की तरफ आप आते हैं ना, उसको हम कहते हैं expansion. Pressure drop, that is known as expansion process. ठीक है? क्योंकि previous में नहीं है, इसमें है. और क्यों, किस तरीके से है, चले हम यहाँ पे जो है ना तो इसको डिस्कस कर लेते हैं. This is the same. You look here. Initially it starts induction from here, okay, then this is a compression process. B to C is the expansion, the delivery process, and C to D is expansion process, and again this is induction, compression, delivery, and expansion process. Okay, now expansion process जो है, that is this compression and expansion, they are polytropic in the first place. ठीक है? तो यहाँ पे what you need to do is, if you want to find out the work consumed by the compressor, तो work consumed ये होगा, अच्छा, area under this curve. ठीक है, this will be actually the work consumed by the compressor. Now you see here why this बाकी चीज़ें तो आपको पता है कि इंडक्शन कैसे होती है, कंप्रेशन कैसे होती है और डिलीवरी कैसी होती है, किस प्रेशर के ऊपर स्टार्ट करता है. बट दिस न्यू थिंग इज अबाउट एक्सपेंशन. हाउ दिस एक्सपेंशन टेक्स प्लेस? इट इज़ वेरी सिंपल. यू नो what happens is if you come here, right, let me rub this a little bit. Okay, when the piston is at the delivery, the compressor is at the end of the delivery stroke. Okay, piston is at the end of the delivery stroke. Okay, now it is start moving from here in the rightward direction. अब यहाँ पे क्या है? Here we are having compressed air in the clearance volume, right? Compressed air in the clearance volume. The moment it starts from this position in the rightward direction, this pressure drops. ठीक है, ये प्रेशर कम होगा ना. Why? Because volume is increasing. Volume increase होगा, pressure will drop, right? This pressure drop is basically your expansion process, which was not the case in the previous scenario, जिसमें clearance volume नहीं था. ठीक है, डायरेक्टली जो है इंडक्शन, then we have compression and then delivery. That's it in the previous case. But in this case, the moment the piston starts moving from the leftward direction to this rightward, what happens is that compressed air is, the pressure of that compressed air is decreased. Why? Because the volume is now increased, so the pressure will increase even if you have PVN is equal to constant or PV gamma is equal to constant or PV is equal to constant. In all the cases, volume increases, the pressure will decrease. That decrease in pressure is basically attributed as a expansion process. तो इसकी समझ आ गई आपको? तो ये जो है ना आपके पास ये एक्सपेंशन प्रोसेस है, बाकी चीज़ें सेम है. चले इसको हम जो है ना यहाँ से देख लेते हैं. C to D, this is C and this is your D. That is what expansion process. The piston begins the induction stroke. ठीक है, इसके एंड के ऊपर इंडक्शन स्ट्रोक स्टार्ट होता है. द कंप्रेस्ड एयर ऑक्युपाइंग द क्लियरेंस वॉल्यूम इसी एक्सपेंड्स ये है टू द पॉलीट्रॉपिक लॉ PVN इज इक्वल टू, ये पॉलीट्रॉपिक एक्सपेंशन है. अच्छा, until the pressure and temperature fall to P1 and T1. ठीक है, ये प्रेशर जो है P2 T2 है and the expansion takes place, the pressure drops, right, to P1 and T1, right, respectively. Ideally there is no heat transfer from the air to the surrounding. ठीक है, ये ट्रांसफर नहीं होता. इंडक्शन प्रोसेस क्या है? इंडक्शन प्रोसेस वही है, ठीक है, लेकिन इसमें इंडक्शन वॉल्यूम कम हो जाएगा. अच्छा, ये यू कैन सी प्रीवियसली वी वर हैविंग दिस मच इंडक्शन वॉल्यूम, right? So you can see here that this is if this is, let's say for example, the total volume of the cylinder, let's say that is VT for example, या VA आप इसको कह सकते हैं, because this is your VA. So the volume that is swept, ठीक है, swept, जिस तरह sweeping नहीं होता, sweeping, ये sweeper जिस तरह करता है, तो this is actually swept, right, by this piston. So यहाँ तक जो है ना ये क्या करता है, ये वॉल्यूम स्वीप करता है, स्वीप करता है, ठीक है, बाहर निकालता है. इसके अलावा ये जो है ना ये वॉल्यूम जितना बाकी रहता है ना, दैट इज योर क्लियरेंस वॉल्यूम. तो दिस इज योर स्वीप्ट वॉल्यूम एंड दिस योर क्लियरेंस वॉल्यूम. सो वी सी इज इक्वल टू द टोटल वॉल्यूम VA माइनस स्वीप्ट वॉल्यूम. ठीक है, और यू कैन से दैट द टोटल वॉल्यूम इज इक्वल टू क्लियरेंस वॉल्यूम प्लस स्वीप्ट वॉल्यूम. ठीक है, ये जो है ना आप देख सकते हैं. इंडक्शन प्रोसेस प्रीवियसली हमारे पास इंडक्शन क्या था? इंडक्शन वाज VA. ठीक है, जितना ये सारा वॉल्यूम जो है ना ये इंड्यूस्ड वॉल्यूम था. अब इस केस में क्या है? इंडक्शन विल बी व्हाट? इंडक्शन इज योर, दिस इज योर VA एंड दिस इज वेयर इज योर VD, दिस वन VD. ठीक है, सो VA माइनस VD इज योर इंड्यूस्ड वॉल्यूम नाउ. ठीक है, VA माइनस VD, दिस इज योर, इतना वॉल्यूम आप इंड्यूस करते हैं. ठीक है, तो ये आप देख लें. द इनलेट वाल्व ओपन्स, फ्रेश एटमॉस्फेरिक एयर इज इंड्यूस्ड इनटू द सिलेंडर एट कांस्टेंट प्रेशर P1 आइसोबैरिक एंड टेम्परेचर T1. तो इतना जो है ना द वॉल्यूम ऑफ एयर इंड्यूस्ड इज VA माइनस VD इन दिस केस. आइडियली देयर इज नो हीट ट्रांसफर फ्रॉम द सराउंडिंग. ये हर केस में होता है हमारे पास, राइट? आइडियली देयर इज बट अ लिटिल बिट. कंप्रेशन प्रोसेस वही आपके पास है. PVN is equal to constant, यही compression path है, delivery stroke भी वही है. The pressure increases from P1 to P2, okay, and the valve will open and it will deliver that volume. तो ये जो है ना आपके पास जो VB है ना, volume VB, this is basically your previously आपके पास जो है ना, this was VB, this is the delivered volume. Now आपके पास क्या होगा, VB minus VC will be the delivered volume, right? तो बहरहाल इसको जो है ना आप खुद से देख सकते हैं, राइट. नाउ मेरे ख्याल में आगे इसको डिस्कस किया गया है, एयर कंप्रेसर विद क्लियरेंस. So they are saying that at the end of the delivery stroke, the clearance volume VC is filled with compressed air at pressure P2 and temperature T2. The cycle is repeated, right? So expansion takes place, and then induction takes place, and the induction volume will be your VA minus VD. Then compression takes place, polytropic compression. This is also polytropic expansion, polytropic compression, induction, and this will be the delivery, and it repeats itself. ठीक है, तो इसकी समझ आ गई आपको. If you remember, हमने ये भी बात की थी कि हमारे पास क्या है, relationship between states. Before this, the relationship between states for air compressor without clearance volume was given as follows. If you remember, ठीक है, ये previous है, free air है P0 by T0, ठीक है, या ये मैंने आपको बताया था. दिस इज बेसिकली वी वांट टू शो दैट दिस इज M0, दिस इज योर M1, mass flow rate is a constant. So how to have this mass flow rate as constant, because PV is equal to MRT है ना, तो M is equal to PV over RT, right? PV is equal to RT, ठीक है. तो यहाँ पे जो है ना आप इसको देख सकते हैं कि भाई P0 will be RT0, P1 ये previous case है, अच्छा remember, without clearance, P1 VA RT1, P2 VB RT2. This was for, you know, without clearance. With clearance क्या होगा, the same thing, but you know, free air the same one, right? बल्कि यहाँ पे same thing. This is P1 by RT1, but what is the induced volume? VA minus VD. अभी मैंने आपको बताया, ठीक है. This is P2 by RT2, the same. What is the delivered volume? That is your VB minus VC. अभी जो मैंने आपको बताया, right? Previously, this whole volume was delivered volume. This one from here to here. This is VB. VB is the delivered volume. Now we have actually a clearance volume over here. So VB minus volume at C. ठीक है, ये क्लियरेंस वॉल्यूम नहीं, यहाँ पे ये सी के ऊपर जो वॉल्यूम है इतना, ये बाकी रह जाता है. तो ये जो है ना आपके पास, दिस इज योर यू नो डिलीवर्ड वॉल्यूम, ठीक है. तो इसमें ये चेंज आपके पास आ जाता है. एनीवेज, देन दे आर टॉकिंग अबाउट द कंप्रेसर कैपेसिटी. ये मैंने आपको बताया था FAD, ठीक है, FAD फ्री एयर डिलीवरी, ठीक है. फ्री एयर डिलीवरी जो है ना आपके पास बेसिकली कैपेसिटी, कंप्रेसर कैपेसिटी इज द रेट ऑफ वॉल्यूम ऑफ एयर डिलीवर्ड. अच्छा, ठीक है. तो ये कंप्रेसर की जो कैपेसिटी है ना, रेट ऑफ वॉल्यूम, वॉल्यूमेट्रिक फ्लो रेट ही है, जितना एयर जो है ना ये डिलीवर करता है ना, उसको हम कहते हैं वॉल्यूमेट्रिक फ्लो रेट. बट इट इज मेजर्ड एट एम्बिएंट कंडीशंस, मैंने आपको बताया था, ठीक है, एंड इज ऑफन एक्सप्रेस्ड एज फ्री एयर डिलीवरी. तो बेसिकली दिस इज वॉल्यूमेट्रिक फ्लो रेट, बट इफ यू सी हियर देयर इज अ नॉट हियर, ठीक है. इसका मतलब ये कि इट इज मेजर्ड एट फ्री एयर कंडीशन. इफ यू रिमेंबर, मैंने आपको बताया था, अच्छा, कि दिस इज द डिलीवर्ड वॉल्यूम, सॉरी डॉट, एंड यू आर मेजरिंग, ठीक है. ये वॉल्यूम जो है ना आपके पास जाता है, लेट्स से फ्रॉम कंप्रेसर, ये जाता है एक वैक्यूम चैम्बर में, एंड यू आर मेजरिंग दिस इन वैक्यूम. दैट विल बी डिफरेंट, अ बिट डिफरेंट, ठीक है. ज़्यादा डिफरेंट नहीं होगा, बट इट विल बी अ बिट डिफरेंट, राइट, बिकॉज यू आर मेजरिंग इट इन द वैक्यूम. सिमिलरली, इफ यू आर मेजरिंग इट अगेंस्ट हायर प्रेशर, it will be different. But if you are measuring this volume, okay, the volume delivered by the compressor at ambient temperature and pressure, उसको हम कहते हैं FAD. तो this is actually volumetric flow rate in cubic meter per minute, but measured at ambient condition. ambient condition का मतलब ये ambient temperature and pressure, इसलिए जो है ना इसको हम free air delivery कहते हैं, FAD. this is actually the term. अच्छा, फिर कहता है कि ये FAD जो है ना, इट डिपेंड्स ऑन सम ऑफ द थिंग्स, ओके. तो जो इफेक्टिव या एक्चुअल FAD होता है ना, वो डिफरेंट होता है, एंड इट डिपेंड्स ऑन, यू नो, डिफरेंट थिंग्स. सो इफ द FAD इज मेजर्ड एट एम्बिएंट कंडीशन, P is equal to P0, फ्री एम्बिएंट प्रेशर एंड टेम्परेचर, विद कंप्रेसर स्पीड, ये इसके ऊपर डिपेंड करता है, राइट. It depends on compressor speed. It depends on the piston type. Compressor type. It is single acting, double acting, and also it depends on the number of cylinders. Okay, तो इन चीज़ों के ऊपर ये डिपेंड करता है. So if you encounter these things and you want to calculate the actual volume delivered per cycle, वो क्या होगा? That will be the if AD divide by ये क्या है? RPM, compressor speed, multiplied by ये multiplied है, multiplied by B, that is the compressor type. Single acting है, so in place of B you can put 2. Double acting है, अगर single acting है you can put 1 in place of B. And similarly this E is for number of cylinders. So this if you know about this FAD, if you know about the RPM, you know about this type of air compressor, and you know about the number of cylinders, you can calculate actually how much air will be delivered. ठीक है, तो ये चीज़ भी आपको समझ आ गई. Then एनालिसिस ऑफ द साइकिल में हम क्या करते हैं कि इन द सेम वे, इन द सेम फैशन यू नीड टू फाइंड आउट द इंडिकेटेड पावर. ठीक है, फॉर द केस विद क्लियरेंस वॉल्यूम. ठीक है, तो एग्जैक्टली वही चीज़ है, मैंने आपको बताया था. देयर इज इवन नो नीड टू एक्सप्लेन दिस. यू नीड टू फाइंड आउट द एरिया अंडर द कर्व फॉर दिस पीवी डायग्राम, दैट्स इट. क्योंकि प्रीवियसली हमारे पास डिफरेंट था, अच्छा अभी डिफरेंट है. ठीक है, इसमें असल में आपके पास ये भी एक एरिया आ गया है, तो ये जो है ना एक्स्ट्रा वो है. लेकिन यू नीड टू फाइंड आउट दिस एरिया अंडर द कर्व इज योर व्हाट इंडिकेटेड वर्क. तो ये क्या होगा? एरिया ए बी सी डी, ए बी सी एंड डी. हाउ टू कैलकुलेट दिस? एरिया ए बी ई एफ, ए बी ई है, चाहिए बात ये वाला ई है, एंड दिस इज एफ. ये एरिया आप मालूम कर लें क्योंकि प्रीवियसली हमने मालूम किया भी है. माइनस एरिया सी ई एफ डी. लुक सी, चले मैं थोड़ा सा ये रब करता हूँ. सी ये ई है, ये वाला ये ई है, दिस वन ई. एफ और डी, ये मैं आपको बता रहा था. अच्छा सी ई एफ डी. तो अगर ये पूरे एरिया से दिस वन एरिया, इससे अगर ये वाला एरिया अगर आप माइनस करें तो ये रह जाएगा ना. तो ये जो है ना हमें रिक्वायर्ड है. तो इसकी ज़्यादा डिटेल में हम नहीं जाते, बार आप खुद जो है ना इसको देख लें कि भाई ये जो है ना विदाउट क्लियरेंस वॉल्यूम है एंड दिस वन इज विद क्लियर. यू कैन सी इंडक्शन वॉल्यूम यहाँ पे कितना था, यहाँ पे इंडक्शन वॉल्यूम कितना है. दिस इज पॉलीट्रॉपिक कंप्रेशन एंड दिस इज पॉलीट्रॉपिक कंप्रेशन. दिस वाज द डिलीवर्ड वॉल्यूम एंड दिस वन इज नाउ द डिलीवर्ड वॉल्यूम इज दिस वन. यहाँ पे कोई जो है ना आपके पास एक्सपेंशन नहीं है, यहाँ पे एक्सपेंशन इज दियर. ठीक है, ये कंपेरिजन है. Okay, you know very well, but just let me tell you that indicated power will be equal to, from that diagram, n by n minus 1 m dot r t2 minus t1. ये जो है ना आपके पास relationship where you can find out the indicated power. ठीक है. अच्छा ये m जो है ना ये इतना वो नहीं है, वो सिंपल m नहीं है, बल्कि this m is basically your mass flow rate at A and mass flow rate at T. इन दोनों का जो है ना ये I should write it like this because ये बिल्कुल प्रीवियस फार्मूले की तरह लगता है. ठीक है, उसमें भी n by n minus 1 m dot r t2 minus t1 था, but here I should write it m dot bar, where m dot bar is basically what? This one. ठीक है जी, बल्कि यहाँ पे लिखा भी है. अच्छा m dot bar is basically the induced mass per unit time. Or this is actually if you want to find out to make it indicated power per cycle in terms of pressure ratios, तो ये भी हमने डिस्कस किया था. अच्छा there is no need to discuss this कि भाई pressure ratio कैसे हम करते होते हैं. ठीक है, you can just take it. So if you know about polytropic index, mass flow rate that you have induced, R is constant, T1 is the initial temperature, you need to know about this, and you need to find you need to know about the pressure ratio. ये तो आपको पता होगा. This is basically the requirement. कितना pressure ratio आपको चाहिए. So if you know about all these things, you can find out that how much indicated power per cycle will be consumed, right? And from here you can even select the motor for this, right? Okay, तो ये इसके ऊपर जो है एग्जांपल 4 है. सिंगल स्टेज डबल एक्टिंग, सिंगल स्टेज है. ठीक है, डबल एक्टिंग है. एयर कंप्रेसर इज रिक्वायर्ड टू डिलीवर दिस मच वॉल्यूम, ओके, पर मिनट, मेजर्ड एट दिस. अच्छा ये देखें, नाउ दिस इज FAD, आई थिंक, because it is measured at what? Atmospheric pressure. ठीक है, या जो एम्बियंट है, और इसके ऊपर ये आपको गिवन है। द डिलीवरी प्रेशर इज 7, तो इसका मतलब ये है कि 7/1.013, दिस इज एक्चुअली योर प्रेशर रेशो P2 by P1, and the speed is 300 rpm and take the clearance volume is 5% of the swept volume। अच्छा, तो swept volume जितना आपके पास है ना उसका 0.5 आप लेंगे, ये आपके पास ये आ जाएगा, क्लियरेंस वॉल्यूम आ जाएगा of the swept volume with compression and recompression index, ये polytropic index की बात कर रहे हैं, n is equal to 1.3, right? Calculate the swept volume, पहले आपने swept volume फाइंड आउट करना है, ठीक है, of the cylinder and the delivery temperature T2 आपने फाइंड आउट करना है, and the indicated power end में जो ये आपके पास है, ठीक है, this is indicated power, ये आपने फाइंड आउट करना है। तो T1 आपके पास है, P2 by P1 आपके पास है, n आपके पास है, एंड मे बी कुछ चीज़ें जो है वो आप T1 आप फाइंड आउट, T2 आप फाइंड आउट कर लें, और जो है ना फिर आपने VS फाइंड आउट करना है, ये आप खुद से कर लें। अच्छा, दिस इज सॉल्व एग्जांपल बेस्ड ऑन द सिंपल रिलेवेंट फार्मूलाज। वॉल्यूमेट्रिक एफिशिएंसी इज डिफाइंड एज द वॉल्यूम ऑफ एयर डिलीवर्ड, कितना वॉल्यूम जो है ना ये डिलीवर करता है, मेजर्ड एट द फ्री एयर प्रेशर एंड टेम्परेचर डिवाइडेड बाय द स्वेप्ट वॉल्यूम ऑफ द सिलेंडर, कितना वॉल्यूम जो है ना ये डिलीवर करता है और कितना जो है ना ये स्वीप करता है, यानी लीकेजेस को, बेसिकली वॉल्यूमेट्रिक एफिशिएंसी लीकेज को इनकाउंटर करता है, ठीक है, कि इतने कितना स्वीप किया वॉल्यूम को, ठीक है, हाउ मच वॉल्यूम इज स्वेप्ट, हाउ मच वॉल्यूम इज स्वेप्ट एंड हाउ मच इट इज डिलीवर्ड, ओके। तो इनका जो है ना आपस में जो रेशो है दैट इज नोन एज वॉल्यूमेट्रिक एफिशिएंसी, बेसिकली लीकेजेस को देखता है। तो इसके दो किस्म के फार्मूले हैं, अच्छा, दो किस्म तरीक़ों से हम इसको कह सकते हैं, एक तो वो है वॉल्यूम डिलीवर्ड बाय स्वेप्ट वॉल्यूम, और दूसरा जो है ना वॉल्यूम इंड्यूस्ड बाय स्वेप्ट वॉल्यूम, ये भी आप कह सकते हैं, ठीक है। तो वॉल्यूम इंड्यूस्ड ये क्या है, VA माइनस VD डिवाइड बाय स्वेप्ट वॉल्यूम, राइट। अच्छा, ये मैंने आपको बताया था कि ये वी स्वेप्ट वॉल्यूम को और डिलीवर्ड वॉल्यूम को जो है ना, सॉरी दिस व्हाट शुड आई से, दिस टोटल वॉल्यूम को जो है ना हम फाइंड आउट कर सकते हैं आसानी से, और इसकी रीज़न क्या है, वो मैन्युफैक्चरर को पता होता है कि भाई टोटल वॉल्यूम ऑफ द सिलेंडर इतना है, तो मैंने जो है ना वो क्लियरेंस इतनी रखी है, तो स्विफ्ट वॉल्यूम जो है ना हमारे पास वो कैलकुलेट कर सकता है 0.6% ऑफ द टोटल वॉल्यूम, या तो ये तो हमें क्लियरेंस वॉल्यूम यहाँ से आ जाएगा, ठीक है, लेट्स से वो 6% क्लियरेंस रखता है, तो दिस विल बी योर क्लियरेंस वॉल्यूम। तो नाउ योर टोटल वॉल्यूम माइनस योर क्लियरेंस वॉल्यूम विल बी योर स्विफ्ट वॉल्यूम। इसका मतलब ये है कि यू कैन कैलकुलेट योर स्विफ्ट वॉल्यूम। सिमिलरली दिस इज द टोटल वॉल्यूम ऑफ द सिलेंडर, ठीक है, ये पता होता है। VD को फाइंड आउट करना जो है ना थोड़ा सा मुश्किल होता है, तो इसलिए मेरे ख्याल में आगे जो है ना इसने क्या किया है, ये VD को किसी और टर्म में जो है ना इसको लेके आया है, ठीक है, तो वो चीज़ जो है ना बहरहाल आप देख लें। सो यू कैन यूज रेडिली दिस फार्मूला टू फाइंड आउट द वॉल्यूमेट्रिक एफिशिएंसी, लेकिन मैं आपको बताया कि VA इज इजी टू फाइंड, VS ये भी आप कैलकुलेट कर सकते हैं, VD जो है ना ये इसको कैलकुलेट करना थोड़ा सा डिफिकल्ट होता है, द वॉल्यूम, द वैल्यू ऑफ द वॉल्यूम हेयर, इसलिए जो है ना आगे जाके इसको सिंप्लीफाई किया गया है। एनीवे, फ्रॉम द रिलेशनशिप एस्टेब्लिश्ड बिफोर, इफ अगर आपके पास P1 और P0 यानी बिफोर कंप्रेशन प्रोसेस ये प्रेशर सेम है और ये प्रेशर भी टेम्परेचर भी सेम है, ठीक है, तो जो आपके पास the volume induced will be this is the volume induced, okay, and that will be equal to this V0, okay, और actual V0 जो है ना हमारे पास किस चीज़ के बराबर होगा, प्रीवियसली हमने देखा, it is influenced by these three things, okay। Therefore for this assumption where P1 is equal to P0 and T1 is equal to T0, आपके पास जो वॉल्यूमेट्रिक एफिशिएंसी है that is the actual volume delivered by the swept volume, कितना जो है ना स्वीप करता है और कितना एक्चुअली ये डिलीवर करता है, that will be your volumetric efficiency. This is one of the relationships, ठीक है। Similarly another relationship is और ये कहता है कि you can see that volumetric efficiency is equal to this VA minus VD induced volume by swept volume, and induced volume you can see that this is VA minus VD, what is your VA मैंने पे आपको बताया था, ठीक है, VA is the total volume, that is actually the addition of swept volume plus a clearance volume, so swept volume plus clearance volume, swept volume is with you, okay, एंड देन फर्दर भी इसको थोड़ा सा सिंप्लीफाई किया गया है. इफ़ यू रिमेंबर प्रीवियसली मैंने आपको रिलेशनशिप बताई थी कि यू कैन रिलेट वॉल्यूम रेशो टू प्रेशर रेशो फॉर पॉलीट्रॉपिक प्रोसेस. ठीक है, इफ यू रिमेंबर प्रीवियस उसमें है आपके पास. तो वी डी बाई वी सी इज इक्वल टू पी टू बाई पी वन वन ओवर एल. इसमें जो है ना वी डी आप निकाल लें. वी डी इज इक्वल टू दिस थिंग. Now you see that we know about polytropic index, we know about our required pressure ratio, and we know about the clearance volume. ठीक है, क्लियरेंस वॉल्यूम मैन्युफैक्चरर को पता होता है. ठीक है, कि कितना परसेंट जो है ना 5%, 6%, 10% of the total volume रखता है. So all these things at right side they are actually known quantities. This means that you can find out the value of VD. ठीक है, तो जिस तरह मैंने आपको बताया था कि it is difficult to find out this VA and VS is simple, but to find out VD is difficult. So for that reason, we have actually converted or we have actually alternate, you know, what should I say, indirectly find out the value of this VD. कहाँ से हम find out करते हैं? Using this relationship. बहरहाल ये जो है ना, you can find out the value of VD and then you know putting it over there. Ultimately, you will see that the volumetric efficiency, another formula, okay, ये 15 भी है और 17 भी है. That is 1 minus VC by VS. Both are either measurable or calculated easily, and this is pressure ratio and this is N. So you can find out the value of volumetric efficiency. Right? There is an example 5, and that is actually your practice example. Okay. तो बहरहाल सॉल्व एग्जाम्पल है, उसको जो है ना आप खुद से कर सकते हैं, इन्हीं उसके ऊपर बेसिस है. राइट. ओके, एग्जाम्पल 6 इज आल्सो देयर. यू कैन हैव द डेटा फ्रॉम देयर एंड यू कैन फाइंड आउट. ये चीज़ भी आप कर सकते हैं. ठीक है. नाउ डिस्कसिंग द एयर कंप्रेसर, reciprocating air compressor with clearance volume. We can also we are now in a position to discuss the multi-stage compression. ठीक है, इसको थोड़ा सा आप देख लें. अच्छा, तो let me explain this with the PV diagram. You see here, सबसे पहले तो ये बात है ना कि why we need multi-stage compression. Multi means more than one, right? So you see here that if you are using a single cylinder, okay, it will cost you, let's say, X. And if you are using 3 cylinders, it will cost you Y. And obviously Y will be greater than X. So you are actually spending money on extra cylinders. That's it. Okay. You are using actually for having 3 stage air compression, you are using, you know, various and more than one cylinders, okay, and more than one stages. So it will cost you. Okay, how you can justify this cost, or how this process of multi-staging is cost effective? ठीक है, इसकी एक रीज़न होनी चाहिए कि भाई हम जो है ना एक सिंगल सिलेंडर में क्यों, लेट्स से फॉर एग्जांपल you want to achieve this pressure ratio P2 by P1. Let's say this pressure ratio is X bar. Now, if you want to achieve this pressure ratio using a single cylinder, a single, you know, stage reciprocating air compressor, what will be the limitations and drawbacks? Okay, that you are flipping from using this single stage to 2, 3 or 4 stage reciprocating air compressor. बात समझ आ गई? तो इसकी रीज़न होनी चाहिए. अच्छा, तो यहाँ पे आप देख लें. सबसे पहली बात तो क्या है, इफ़ यू सी हियर, ये यहाँ पे इस तरह डिटेल से लिखा गया है. आई एम जस्ट पॉइंटिंग आउट द इम्पोर्टेंट थिंग्स. सबसे पहले तो ये है कि इफ़ यू वांट टू इंक्रीज द प्रेशर रेशो, ठीक है, आप पहले आपके पास यू नीड, लेट्स से फॉर एग्जांपल P2 by P1, that is X. आप कहते हैं कि भाई I want this P2 bar by P1 that is greater than इसका EY है. हम कहते हैं कि ज़्यादा प्रेशर रेशो मुझे चाहिए. ठीक है, then I want even more pressure ratio than this one. Let's say P2 double bar by P1 double bar or prime. This is your Z. and this z is greater than y is greater than x. Okay, so you want more and more pressure ratio. And if you are using the single stage compressor, what will be the limitation and drawback and hazards? Okay, and then you will flip that actually compels you to flip or to use the multi stage cylinders. तो ये चीज़ जो है यहाँ पे समझ लीजिए। तो सबसे पहली चीज़ क्या है, अभी हमने पढ़ा है कि वॉल्यूमेट्रिक एफिशिएंसी इज it is induced volume by the swept volume. Now look, let's say for example this is the same PV diagram where the effect of increasing the delivery pressure on the volume of fresh air induced is shown here. तो डिलीवरी प्रेशर जो है ये लुक P1 जो है तकरीबन सेम ही होगा, बल्कि सेम ही है, P1 इज द सेम। डिलीवरी प्रेशर जो है ना वो चेंज होता है, पहले P2 था, देन P2 बार एंड देन P2 डबल बार। सो इफ यू सी हियर in this first case, this is basically your, you see, dA is the induced value, this is your VD, this is your VA, and we will be having VA minus VD, that is what, that is here the induced volume, so volume is the same, let's say. Now so this is actually compression and then it is delivery and this one is expansion for this first case. If you want to if you don't want this P2, rather you want P3 or P2 bar, ठीक है, तो इसके लिए आपको क्या करना होगा, this is your let's say induction initially, and this will be your compression, this is your delivery, and again this is your expansion. Now you can see that this time your induced volume is d bar minus dA, ठीक है, so your induced volume decreases. Again if you are further increasing this, you want this more pressure, ठीक है, pressure ratio, so this will be your compression process, this is delivery, and this one is expansion. Okay, so d double bar, sorry, dA minus d sorry, this VA minus VD double bar, this is now the induced volume, ठीक है. So you can see that increasing pressure ratio, the induced volume is decreased for the same initial pressure. तो आपके पास क्या होगा कि ये swept volume is the same, the clearance volume is the same, and by increasing the pressure ratio in the same single stage or single cylinder reciprocating air compressor, the induced volume decreases, ठीक है, ये induced volume decrease होता है. In case of P2 by P1 it is this one, in case of P3 by P1 it is reduced, in case of P4 by P1 it is reduced further. इसका क्या मतलब है कि the numerator is decreased by increasing the pressure ratio. So आपके पास क्या होगा, volumetric efficiency which is one of the parameter, ये भी decrease होगी, and we don't want this, ठीक है. तो इसलिए जो है ना हम सिंगल स्टेज सिलेंडर में या सिंगल स्टेज में ज़्यादा कंप्रेशन रेशो अचीव नहीं कर सकते. दिस इज वन ऑफ द रीजन वन. दूसरी बात ये है, इफ़ यू रिमेंबर प्रीवियसली, अभी मैंने आपको बताया इसी क्लास में कि इफ़ यू यूज PV इज इक्वल टू कांस्टेंट, दैट इज व्हाट, that is if you want to ensure or if you can ensure that the process of compression is isothermal, so you can say that you can consume or the compressor will consume less work. ये भी अभी हमने बात की. Now how to achieve this, इसके लिए हमको क्या करना पड़ेगा, वेरी सिंपली कूलिंग करनी पड़ेगी, बिकॉज आपने TS डायग्राम में देखा, ठीक है, this was actually the TS diagram that we saw earlier, that you see where is that, somewhere here, ठीक है, यहाँ पे भाई, this is your T1 and this is your T2 bar, and you see that T1 is equal to T2 bar. This means that all the way you are basically cooling this air. तो थोड़ा प्रेशर ज़्यादा होता है, you can cool this, टेम्परेचर भी ज़्यादा होता है, and you can then cool this to the initial temperature, ठीक है. तो ये जो constant cooling process है, it is not efficient in a single stage, ठीक है ना, single stage में efficient नहीं है, you cannot efficiently achieve the cooling process in a single cylinder or in a single stage, ठीक है, तो complete intercooling जो है ना आप नहीं कर सकते, so for that reason हम, और वो हमें चाहिए to make the process nearly isothermal, so for that reason you use a two stage or three stage compression process. So this will be your suction. This is a schematic. Okay, suction at low pressure, and this is the compressor. Then it will have a discharge at medium pressure, and then this discharge will be suction for this one, and this will be the discharge from the second one, and that the pressure P3, let's say for example, to this P1, that will be your pressure ratio. Okay, so you can see that in between these two you can dedicatedly use the heat exchanger over here. Okay, so you can achieve this isothermal process, right? तो ये यहाँ पे ये डिस्कस किया गया. अच्छा, बहरहाल दिस सिचुएशन मल्टी स्टेज कंप्रेशन, राइट, तो ये बताया गया है कि दिस सिचुएशन कैन बी इम्प्रूव्ड बाय परफॉर्मिंग मल्टी स्टेज कंप्रेशन. ऑब्जर्वेशन क्या है कि आफ्टर द फर्स्ट स्टेज कंप्रेशन द एयर इज पास्ड इनटू अ स्मॉलर सिलेंडर इन व्हिच इट इज फर्दर कंप्रेस्ड टू डिजायर्ड फाइनल प्रेशर. The cycle assumes that the delivery process of the first stage and the induction process of the second stage take place at the same pressure. अच्छा, ये assume करता है. अच्छा, assume क्या मतलब, हम कंसिडर करते हैं कि भाई ये जो discharge of the first and induction suction of the second, they are actually at the same pressure. इसको हम PI कहते हैं, intermediate. This is your P1, this is your P2, this is your PI. लेकिन obviously there will be a pressure loss inside this ducts. लेकिन कहता है कि इसको जो है ना हम क्या करते हैं, as opposed to the pressure increment or the pressure increase in these cylinders, okay, or in these compressors, ये जो pressure drop है ना ये वाला inside this duct, these duct, it is very small. So for that reason, although यहाँ पे जो PI होगा ना वो यहाँ पे आके ये PI इस तरह नहीं होगा, ठीक है, it will be different, but they are considering that this is the same. ये बात कर रहे हैं. अच्छा, ये PI के बारे में, ठीक है. तो देखें एडवांटेज क्या है, ईच सिलेंडर वर्क्स विद लोअर प्रेशर रेशो. एक सबसे पहले एडवांटेज क्या है, अगर डबल सिलेंडर, अच्छा दो चीजें हमने डिस्कस की. वन, टू अचीव PV is equal to constant. Second thing is that volumetric efficiency decreases, which is not good, ठीक है. फिर थर्ड चीज जो है ना क्या है कि लेट्स से फॉर एग्जांपल योर प्रेशर रेशियो इज P4 बाई P, बल्कि चले P3 बाई P1, राइट, एंड दिस इज लेट्स से फॉर एग्जांपल 100 बाई 1 बार. अब ये क्या है, फॉर एग्जांपल नाउ दिस 100 बार हाई प्रेशर यू आर वर्किंग विद, or the system is under the influence of high pressure ratio, that is hazardous, you know that, right? Hazardous एक लिहाज से है 1, and then to keep that pressure, okay, you need to have these cylinders, okay, and these compressor made of a very sophisticated material that can withstand this pressure, okay, and this is even hazardous to the operator also. तो ये जो है ना इसका एक ड्रॉबैक है. Now if you are reducing, or if you are using multi-stage compression, तो आप क्या करते हैं, 1 to 50 bar in first stage and 50 to let's say 100 bar in second stage. Now what is your pressure ratio inside or in a single stage, that is your 50 by 1, okay, so it is not hazardous, you have actually reduced that to half almost, ठीक है. तो इसलिए जो है ना it is actually not hazardous, one. And the second thing is that you can reduce the material cost, okay, जिससे आपने ये चीज बनानी है. बहरहाल they are saying that you see here D to A is a two stage में. अच्छा, D to A is induction, then B compression process, then C to B to C is delivery, but that delivery is basically this induction to the second, okay, so A double prime, B double prime, yeah, B prime, C prime, and this one, okay. So you can see that this is actually stage 1 and this is your stage 2. You need to calculate this area, this will be the work consumed by the compressor 1 and this will be the work consumed by the compressor 2, and practically you can see and you will see that if you can achieve the isothermal process, the work consumed by this and this plus this will be less than the first one, ठीक है, तो एक तो जो है ना मटेरियल जो आपके पास है, द सिस्टम इज नॉट हैजर्डस, वन. सेकंड थिंग इज दैट यू आर नॉट लूजिंग द वॉल्यूमेट्रिक एफिशिएंसी, ठीक है, टू मच. इसलिए जो है ना आपके पास जो है वो यू आर, बिकॉज यू आर हैविंग द सेम वॉल्यूमेट्रिक एफिशिएंसी. अच्छा, इनिशियली ये लेता है, ये करता है, ये इसको अगेन देता है, एंड दिस इज एक्चुअली डिलीवरी, अगेन इट इज हैविंग एक्चुअली द सेम थिंग. ये इंडक्शन वॉल्यूम जो है ना आपके पास ये आता है, एंड फॉर दैट रीजन एट सम पॉइंट यू विल आल्सो सी दैट कि हमारे पास जो है ना इंटरकूलिंग प्रोसेस बिटवीन स्टेजेस, ये आपके पास P1 T1, दिस इज PI TI, ठीक है, ये TI है, it should be TI, I think. This is intermediate pressure and intermediate temperature after first stage of low pressure compressor, and then you know there is a dedicated heat exchanger or intercooler installed here. ये काम जो है ना आप सिंगल स्टेज में नहीं कर सकते, ठीक है. तो इसलिए जो है ना दिस इंटरकूलिंग प्रोसेस मेक्स दिस, दे आर सेइंग दैट दिस इज आइडियली यू नो दिस इज supposed to be PI, but this TI is reduced to what, to T1, ठीक है. T1 क्या मतलब है कि the pressure was increased from T1 to TI, but using this intercooler it is again converted to T1, ठीक है, and you are actually having this. तो ये इंटरकूलर भी होता है, एंड समटाइम्स आफ्टर कूलर्स आर देयर. सीएनजी पंप्स में शायद आपने देखे होंगे कि they have actually delivering this at P2, but at T2 increased temperature, then they are actually using this after coolers in order to have this, yes, P2, but this one is at T1 etc. या इस तरह का आप कर सकते हैं, ठीक है. इसलिए जो है ना आपको ठंडी और मयारी गैस दस्तयाब होती है किसी भी उसके ऊपर सीएनजी स्टेशन के ऊपर, राइट. एनीवे यहाँ से जो है ना यू कैन फाइंड आउट, ये एग्जैक्टली यही चीज़ है. अच्छा, ये मैंने आपको बताया कि यू नीड टू फाइंड आउट वर्क ऑफ दिस एंड दिस वर्क ऑफ दिस, ठीक है. तो ये आप मेरे ख्याल में फाइंड आउट कर सकते हैं. इसमें सिर्फ ये होगा कि यहाँ पे प्रेशर जो है ना आपके पास PI है, दे आर यूजिंग द सेम फार्मूला. अच्छा, दिस इज PI, तो दिस इज एक्चुअली द सेम फार्मूला, राइट. दिस इज PI by P1, और इसके लिए P2 by PI होगा, बाकी सेम फार्मूला है. ये यहाँ पे शायद कहीं हमने दिखा ना, वेयर वाज दैट, समवेयर, मेरा ख्याल है कि ये इज द सेम थिंग, राइट, इंडिकेटेड वर्क पर साइकिल. सो दिस इज बट यू नो दे हैव एक्चुअली डिवाइडेड दिस इनटू टू स्टेजेस, राइट. ये बात भी समझ आ गई. ये भी आपको ये वही चीज़ है. अच्छा, intercooling process between stages with multi-stage compression, the air can be cooled as it is being transferred from one cylinder to the next by passing through intercooler, dedicated intercooler. The process of cooling the air is called intercooling process, and with intercooling process a saving in indicated work. Intercooling process से क्या होगा आपके पास, the process will be nearly equal to what, to PV is equal to constant. और ये हमने पढ़ा है कि भाई अगर intercooling होगी, the process will be, or it will tend toward this PV is equal to constant. And if you are having this type of compression, previously we discussed that the work consumed will be less, ठीक है. तो ये चीज़ जो है ना आपकी समझ आएगी. दूसरा ये भी आप देख लें. अच्छा, you can see this cylinder, this stage is a bigger in size than this one, और उसकी रीज़न आपको पता है. अच्छा, क्योंकि इसका इंड्यूस्ड वॉल्यूम ज़्यादा है, फ्री एयर इंडक्शन करता है. The delivered volume of this stage 1 is the induced volume of this stage 2, which is basically compressed. ये compressed है. compressed का क्या मतलब है कि वॉल्यूम रिड्यूस होगा. तो ये रिड्यूस्ड वॉल्यूम जो है ना इसमें जाता है, तभी जो है ना आपको ये बड़ा और ये छोटा नजर आएगा किसी जगह के ऊपर भी, ठीक है, राइट. कंप्लीट इंटरकूलिंग का क्या मतलब है, ये मैंने आपको पहले भी बताया था और अभी बता रहा हूँ. कंप्लीट इंटरकूलिंग का मतलब ये है, दिस वन, यू हैव लेट्स से PI and TI here. So before intercooling or intercooler, after intercooler if you have PI but T1, ठीक है. तो इसका मतलब है ये आपने क्या किया है, T1 is this one, इसको कहते हैं कंप्लीट इंटरकूलिंग. मेरे ख्याल में TS के ऊपर शो भी किया भी होगा, ठीक है. लो सी, ये अल्टीमेट प्रेशर क्या है, P2 by P1. So P1 to PI, then intercooling, complete intercooling. What is this? This is T1. this is TI, right? तो you can see that complete intercooling जो है ना आपके पास क्या है, TI is equal to T1 is equal to TI, और फिर मैंने आफ्टर कूलर बताया था आपको T2 के ऊपर जो है ना आप दिस विल बी योर T2 and this will be your P2. P2 is the required pressure, but T2 is not required, so you are using this after cooler. After cooler again जो है ना इसको T1 के ऊपर लेके आता है, ठीक है. So you can see that the temperature that before compression it was there, that is T1. Even after the compression process and after you achieved the required pressure, it is again T1, ठीक है. तो इसलिए जो है ना ये चीज़ आपके पास है, right? So I think this is the end of today's lecture, and we have multi-stage compression. Inshallah, in the next class, we will talk about the other type of positive displacement machine, and that is what? That is rotary machines. Okay, so we will discuss about the working principle and maybe some relevant formulas, and at the end, I think we will be discussing about the air motor also. Inshallah, in the next class, we will be, you know, we will try to end up with this chapter. Acha, there is an announcement. Remember, most probably, बल्कि most probably क्या कि I should announce that when we will complete this chapter 12, okay, maybe in the next class. So after that week, okay, there will be a quiz in your relative classes. सेक्शन सी की अपनी क्लास होगी, सेक्शन जो बाकी सेक्शन है उनकी अपनी क्लासेस में there will be quiz, ठीक है. क्विज जो है ना उस तरीके से नहीं होगा, because I'm just feeling that that is not the proper way that we are giving actually quizzes and something like this. The quiz will be like this, that it will be sort of viva, ठीक है. The students in the class, that will be, you know, we'll be having an interactive session, and I will ask from the student in the topic that we have studied earlier, ठीक है. चैप्टर 9, 10 और 12 में जो है ना उनसे कोई भी मैं सवाल कर सकता हूँ, and they need to answer me, and I will on the spot you know, assign marks to that student. Okay, so we will be having these types of quizzes in this session, and 2 assignments will be there. So this is actually the sessional work, and you know very well that this sessional work is actually of 30 marks. Okay, that is even having greater percentage than your midterm exam. तो इसके लिए ऐसी ही तैयारी उसी तरीके से आप स्पिरिट के साथ करेंगे जिस तरह आप midterm को करते हैं, बल्कि उससे ज़्यादा जो है ना इसके ऊपर मेहनत करेंगे, ठीक है. So I will announce on your Google Classroom for each and every section in their respective class there will be a quiz, and that quiz will be of this type, that I will ask question from you and I will assign you marks at that particular time, ठीक है. So ये quizzes इस तरह होंगे. Assignment obviously मैं फिर आपसे बाद में लूँगा, and that assignment will maybe one in your chapter 11 and एक assignment जो है वो chapter 13 में होगा, right? तो ये चीज़ आपके जहन में हो. Okay, you can listen to this lecture, and I also uploaded the slides on your Google Classroom, and if you feel any problem then you can contact me, right? तो मैंने कहा कि आपका टाइम जो है ना वो ज़ाया ना हो, इसलिए जो है ये लेक्चर मैंने although there are no classes were there, but actually I found some time, so मैंने कहा कि ये लेक्चर जो है अपलोड कर लें ताकि आपका जो है ना ये वीक ज़ाया ना हो, right? ओके जी, अल्लाह हाफिज़.